A tiny magnet can pick up a paperclip, and that magnet is fighting the whole Earth. The entire planet is pulling down on that clip, and the magnet wins. That's a strange thing to notice, because gravity shapes galaxies. It holds the cosmos together. But here, on this table, it's the weakest thing. It's incredibly weak. Why is that? It's one of the deepest mysteries in physics. This question, why gravity is so weak it challenges everything, our most fundamental ideas about reality. It makes us ask if gravity is even a force, a real force. It points to hidden dimensions. The silence of gravity, its feebleness, it might be telling us something about the true architecture of the universe, what it's built on. So what does it mean that the force holding your world together, the force that built the planets and the stars, is the weakest one you'll ever touch? This cosmic hierarchy isn't just a list. It's the rulebook of reality. To see how strange it is, you need the four fundamental players. First, the strong nuclear force. It's the Titan, the ultimate cosmic glue. It works only inside the nucleus, holding protons and neutrons together. Its strength is almost unimaginable. It has to overcome that fierce repulsion between positively charged protons crammed together. Without it, no atom heavier than hydrogen could exist. The universe would be a sea of single protons and lonely electrons. No stars, no planets, no us. Then there's electromagnetism. It's the architect of our everyday world. It governs light, chemistry, the very structure of matter. It binds electrons to nuclei to form atoms, and atoms together to form molecules. It's what makes a magnet lift a paperclip, defying the entire Earth's gravity. It's about 100 times weaker than the strong force, but its influence is infinite in range, shaping the structure of galaxies just like gravity does. Next, the weak nuclear force. It's the specialist, the cosmic alchemist. It doesn't bind things together. Instead, it changes one type of subatomic particle into another. This process, radioactive decay, is essential. It powers the sun's furnace by converting hydrogen into helium, and it forged the heavier elements in ancient stellar explosions. It's about 1,000,000 times weaker than electromagnetism, and its range is vanishingly small, confined to a distance 1,000 times smaller than a proton. And then, at the very bottom of this list, you find gravity. It's the ghost. It's weaker than the weak force by a factor of 1,000,000 billion billion billion. Let that number sink in. It's not just a little weaker. It's almost not there at all. So this is the hierarchy. The strong force builds the atomic cores. Electromagnetism builds the atoms and molecules. The weak force transforms them. And gravity. On the scale of atoms and molecules, gravity is utterly irrelevant. It's a background hum, a faint suggestion, completely drowned out by the roaring symphony of the other three. Its power only emerges when you gather an almost inconceivable amount of matter in one place. A planet's worth, a star's worth, a galaxy's worth. Only then does its gentle, persistent pull add up to something that can bend the fabric of space and time itself. So the puzzle isn't that gravity is weak. The puzzle is why there's such a staggering, incomprehensible gap between it and everything else. Why is the force that sculpts the grandest structures in the cosmos the feeblest one in the quantum realm? This hierarchy is the first and greatest clue that something profound is missing from our picture. 10 to the 36. That's not just a number, it's a chasm. Take two protons. They're identical fundamental particles. The electromagnetic repulsion between them, because they're both positive, it's a fierce shove. Now compare that to their gravitational attraction, the gentle pull. The electromagnetic force is stronger. Not by 1,000, not by 1,000,000. It's 10 to the 36 times stronger. That's a 1 with 36 zeros after it. A number so large it loses meaning. It's the difference between the energy of a single, quiet breath and the total, raging output of our sun over its entire 10 billion year life. That's the scale. Gravity isn't just the quiet one. It's whispering in a stadium during a roaring concert. And that forces a question: if gravity is this weak, how does it run the universe? How does this faint whisper orchestrate galaxies? The answer is in its character and in the sheer scale of things. The other forces have opposites. Electromagnetism has positive and negative, they can cancel. The strong and weak forces are confined to tiny nuclear distances. But gravity only has one sign: attractive. It never cancels, it only adds. And while a single proton's gravity is nothing, a planet is made of a nearly uncountable number of protons, neutrons, electrons. All their tiny pulls add together steadily across the vast emptiness. There's no shield from it, no anti-gravity to block it. So over astronomical distances with astronomical mass, this incredibly feeble force becomes the only force that matters on the grandest stage. It's the ultimate cumulative effect. But that explanation, while true, it only deepens the mystery. It explains how a weak force can have large-scale consequences, but it doesn't explain why it's so weak to begin with. Why is the fundamental constant for gravity, the number that sets its strength, so infinitesimally small compared to the others? This isn't a question of accumulation. This is a question of origin. It points to the possibility that our understanding of gravity's nature is incomplete, that we're missing a fundamental piece. The difference is staggering. It's more than just a curiosity, it's a crisis for our theories. In physics, when a number in your equations has to be set to an incredibly specific, tiny value for the universe to look like this, that's called fine-tuning. It feels arbitrary, like a dial on a cosmic control panel turned to a precise, unlikely setting. And the strength of gravity is the most extreme example of fine-tuning we've ever seen. Why would nature choose a gravitational constant that's 10 to the 36 times smaller than the electromagnetic constant? There's no reason in our current models. It just is. This is the hierarchy problem, the problem of naturalness. The universe, with all its elegant laws, shouldn't rely on such a fragile, precise balance of numbers to exist. It feels unnatural, like finding a pencil perfectly balanced on its tip in a hurricane. It suggests something is propping it up, something we can't see. This fine-tuning is a powerful clue that our picture is incomplete. The standard model of particle physics, our catalog of particles and forces, works perfectly for the strong, weak, and electromagnetic forces. But it has no answer for this. Gravity's weakness is a screaming anomaly in an otherwise harmonious theory. It's the clearest sign we have that we're missing a deeper layer of reality. A hidden principle, or a new realm of physics, that would make this vast difference feel inevitable, not accidental. The silence of gravity isn't empty. It's full of questions. It's pointing us toward the next great frontier. Gravity follows a completely different set of rules. Take a magnet. It has a north pole and a south pole. Opposites attract, but likes will repel each other. You can put up a shield, a barrier that blocks it. Electromagnetism is like a conversation, a back and forth. But gravity is a monologue. It only does one thing, it only ever pulls. There's no such thing as negative mass, no way to turn it off. You can't build a box to keep gravity out. It just goes through everything. The ground, the air, even your own body. Nothing resists it. That's the first strange thing about it. It's universal, and you can't shield anything from it. Every piece of matter feels it, and every piece adds to it. And that sameness is its real power, because it only adds up. It never cancels out. For two protons, that addition is a tiny whisper, easy to miss. But then you start adding, you get a mountain's worth of protons, a planet's worth, a star's worth. All those tiny whispers become one single, overwhelming roar. The other forces, they cancel each other out or they stay in their own small domains. The positive and negative charges on a planet basically balance, so its net electromagnetic pull over distance is almost nothing. But every single atom in that planet is singing the same gravitational note, in the same direction, and that chorus just keeps building. It never stops. That's why gravity wins at the cosmic scale. It's not because it's strong. It's because it's patient and persistent, and it's completely unanimous. Its weakness is actually why it can dominate. A force that pushed and pulled would create a balanced, static universe. But a force that only pulls and pulls on everything ends up gathering all the scattered pieces of the cosmos. It pulls them into these huge, swirling structures. So you have this dual nature. It's so weak it's negligible, yet so inescapable it shapes everything. And that forces a different thought. Maybe we've been thinking about gravity the wrong way. We call it a force like the others, but what if it isn't a force at all, not in the traditional sense? What if its unique character comes from it being something else completely? Something more fundamental, woven into the very fabric of the stage where everything else plays out. So there's this ghost in the quantum machine, the graviton. In the very small world, forces don't just happen, they have messengers. You can picture two skaters on a frozen pond. If one throws a heavy ball to the other, they both recoil. They're pushed apart. That exchange of an object it mediates a repulsive force. Now, if they caught a boomerang instead, something that pulled them together as it passed, that would mediate an attraction. In the quantum realm, it's the same. The electromagnetic force is carried by the photon, the particle of light. The strong nuclear force is carried by gluons. These messenger particles are constantly exchanged. They create the pushes and pulls we see. For gravity to fit into that quantum framework, it also needs a messenger. Physicists call that hypothetical particle the graviton. Its properties come from gravity's own character. Because gravity affects everything with mass and energy, the graviton has to couple to all forms of energy. Because gravity is always attractive, the graviton must have an even quantum spin, specifically spin 2. And because gravity's influence travels at the speed of light, the graviton, like the photon, has to be massless. But this is where gravity's staggering weakness writes itself into the particle's nature. That coupling constant, the number that describes how strongly the graviton interacts with other particles, it's astronomically tiny. So small that the probability of a single graviton interacting with a particle in a detector is almost zero. To even have a chance of seeing one, you'd need a detector so massive and sensitive it borders on the absurd. Maybe a planet-sized instrument made of pure crystal, waiting for a tremor from the cosmos. And this isn't just a technological hurdle. It's a fundamental statement about gravity's place in the quantum world. The other forces shout their presence through their messengers. You see them easily in particle colliders. Gravity whispers. Its messenger is a ghost. It passes through the universe almost entirely unnoticed. It leaves only the faintest trace in the bending of spacetime itself. That elusiveness, it's why a true quantum theory of gravity, like string theory or loop quantum gravity, stays in the realm of beautiful mathematical speculation. We have brilliant ideas, but the messenger we need to confirm them hides in the silence of its own incredible weakness. That's the Planck energy. It's a threshold. A doorway into a kind of physics we've never actually seen. To get a sense of it, you take a proton's mass energy, the energy equivalent of its existence from Einstein's equation. The Planck energy is 10 to the 19 times larger than that. A 1 with 19 zeros. An energy so huge it doesn't have any comparison here. It's the energy where, according to our theories, the quantum nature of gravity can't be ignored anymore. Where spacetime itself, that smooth fabric, should start to churn, to foam with quantum uncertainty. It's where all the forces might finally speak one language. But that leads to something profound and frustrating. Our most powerful machine, the Large Hadron Collider, it smashes protons together at energies that are just a whisper. Compared to that cosmic roar, to reach the Planck scale, you'd need a particle accelerator the size of a galaxy. It's completely beyond us, so we're left probing a universe where gravity's quantum face is veiled, hidden behind an energy barrier we can't imagine. And that's the direct link to gravity's weakness. That staggering number, 10 to the 36, it's not random. In our models, it's the square of the ratio between the energy of our everyday world and this colossal Planck energy. Gravity feels weak because the energy scale of our existence is so small. Infinitesimally small, compared to the energy where gravity becomes its true, unified self. It's like hearing a symphony from a distant room, through walls a mile thick. All we catch is the faintest, deepest bass note. The full complexity of the music is lost, and that leads to a thought. There was only one moment in the entire history of the cosmos when energies everywhere routinely matched the Planck scale. The first instant of the Big Bang. In that primordial fire, for a time so short our numbers can't really describe it, gravity would have roared, with a strength equal to the other forces. Its quantum nature would have been the dominant feature of reality. The universe began in a state of perfect, symmetrical unity. And gravity's profound silence today is the echo of that symmetry breaking. Freezing into the quiet, persistent pull we feel now, across the cold, vast expanse of space and time. The weakness of gravity might be an illusion, it might not be faint at all. We could just be seeing a fraction of its strength. That's where geometry comes in. The geometry of reality. String theory suggests something. It suggests our universe, with its 3 space dimensions and 1 of time, might be a slice. A membrane, floating in a larger space with more dimensions. You can think of it like a pond, a vast, still pond. Imagine you're a tiny creature living on the surface. Your world is 2-dimensional. Forward, backward, left, right. You have no concept of up or down. Now a stone drops into the water. From your flat perspective, you see ripples. Circles spreading out. The energy of the impact seems to dissipate. It spreads quickly across the surface, but a bird above sees the truth. The stone's energy didn't just go across the surface. It sent waves deep into the water, into that 3rd dimension you can't perceive. From your limited view, the effect seems diluted. The energy is spread thin. That's the core idea. In string theory, our universe is that pond surface. It's called a brane. The higher dimensional space it floats in is called the bulk. And here's the twist. The particles that make up everything we see, quarks, electrons, photons, they might be vibrations trapped on the brane's surface. They can't leave, but gravity is different. Gravity is the curvature of space-time. It could be like those ripples. It can leak off our brain. It can propagate into the extra dimensions. Into the bulk. From our 3-dimensional perspective, this leakage would make gravity seem weak. Incredibly weak. Its strength isn't gone, it's just spread out. Diluted across a hidden cosmic volume we can't see. So the hierarchy problem gets a geometric answer. Gravity isn't weaker by some random accident. It appears that way because we only intercept a tiny fraction of its full force. The rest flows into dimensions. Dimensions curled up or extended beyond our perception. It's a reframing. The force that feels like a whisper here might be just as loud as all the others in the full architecture of reality. We're living in the quiet corner. A quiet corner of a much grander, multidimensional cosmos. A fraction of a millimeter is something you can see. It's the width of a human hair. The thickness of a grain of sand. And the idea is that extra dimensions, if they exist, might not be tiny loops. They could be enormous on a human scale. Large enough to walk across if you could step out of our reality. This is called the ad scenario for the physicists who came up with it. It flips the logic. If gravity is leaking into these large extra dimensions, then its weakness here in our 3-dimensional slice has a cause. The force isn't faint. It's just spread thin. Spread across a wider space, and that leads to a prediction. If you could measure gravity with enough precision over very small distances, you might catch it. On scales larger than a millimeter, gravity follows Newton's law, the inverse square law. The force weakens with the square of the distance. But if there are large extra dimensions, then on scales smaller than that dimension size, gravity could change. It could follow an inverse cube law, or a higher power. In that tiny realm, gravity would stop being the weakest force. It would become stronger, much stronger as you probe closer. Because you'd be getting nearer to the source before its influence leaks away. This isn't just theory. It's tabletop physics. In labs, scientists use devices of breathtaking sensitivity to hunt for this deviation. The most famous are torsion balances, a bar hanging from a thin fiber, at each end a small test mass. Then you bring another large mass incredibly close to one of them. A hair's breadth away, you measure the twist in the fiber, the almost imperceptible pull of gravity. The entire apparatus is shielded from every vibration, every stray electric field, every breath of air. The goal is to see if gravity's pull at 1/10 of a millimeter matches our three-dimensional world, or if it suddenly becomes stronger, revealing an extra dimension. So far, no deviation has been found. Gravity obeys the old rules down to scales smaller than a human hair. But the search goes on, pushing into more microscopic domains. Each negative result is not a failure, it's a map. It tells us where the large extra dimensions are not. It shrinks the possible hiding places. The connection is the profound beauty. A grand idea about the fundamental weakness of gravity makes a specific, fragile prediction you can look for on a tabletop. It ties the fate of galaxies to the quiet twist of a wire in a silent room. The silence of gravity might be the very thing that teaches us to listen. The Randall-Sundrum idea is different. It's not about a large, flat extra dimension. It's about a deep canyon, a warped one. Our universe is a brain, a slice of reality, but it sits at the edge of a fifth dimension. And this dimension isn't a simple line. It's exponentially curved, warped. You can picture two sheets of paper. They're flat. They represent two brains. And you put them at opposite ends of a long, narrow valley. The valley floor isn't level, it slopes steeply, it's warped. The distance between the two sheets is short, but the terrain between them is extreme. So a signal from one to the other would be distorted, weakened. In this model, gravity is fundamentally strong. It's true, quantum strength exists at the other end of that warped canyon, on a different brain. But the warping of the space in between acts like a filter, an exponential dampener. By the time gravity's influence reaches our brain, it has been suppressed by that immense curvature. It's been diluted, not by spreading out, but by traveling through a distorted landscape. The consequence is this: the fundamental scale of gravity, the energy where its quantum nature becomes obvious, could be much lower. Not the unreachable Planck energy. It could be at the tera-electronvolt scale. That's the energy realm of our largest particle colliders. That changes everything. It means the hierarchy, that staggering gap, isn't a feature of gravity itself. It's an artifact of our place in a warped geometry. We live in the quiet suburb of a much more energetic cosmos. And this leads to a prediction. If the warping is right, and the true quantum gravity scale is within reach, then our colliders might not just find new particles. They might create something more exotic. In a high-energy collision, if two particles slam together with enough concentrated energy, they could, for an instant, warp local spacetime so severely they pinch off a tiny, microscopic black hole. A mini black hole. It would be fleeting, evaporating in a flash of radiation via Hawking's process, but its creation would be a direct signal. Proof that we've touched the quantum fabric of gravity. That we've briefly accessed the warped geometry that shapes our reality. So there are two geometric answers. One with large, flat extra dimensions where gravity leaks away. And one with a single, warped dimension where gravity is filtered. Both use the shape of hidden reality to explain a mystery. Both turn weakness into a clue. A clue written not in force but in form. There's another number. It makes the hierarchy problem look small. This is the worst prediction science has ever made. In quantum field theory, the vacuum of space isn't empty. It's this seething sea of virtual particles. They flicker into existence, borrow energy, then vanish. That activity gives the vacuum a fundamental energy, a baseline hum, and through Einstein's equations, that vacuum energy should have a gravitational effect. It should act as a cosmological constant, a kind of anti-gravity pushing space apart. But the scale is the problem. When you calculate the expected density of this vacuum energy, the number is monstrous. It comes out 1 with 120 zeros larger than the tiny acceleration we actually see. The prediction is off by 10 to the 120th power. That isn't just wrong, it's catastrophically wrong. It means the universe should have torn itself apart instantly, in a violent expansion, yet here we are. In a universe that only now, after billions of years, is beginning a very mild acceleration. This isn't a small error, it's a screaming contradiction. Between our two most successful theories, quantum mechanics and general relativity, and at the heart of it is gravity's unique sensitivity. Gravity couples to all forms of energy. Unlike any other force, it feels the hum of the vacuum. It should respond with overwhelming force, but it doesn't, it responds with a whisper. So that means one of two things. Either our understanding of the vacuum's energy is fundamentally flawed, or there's a miraculous cancellation. A fine-tuned balance where the positive energy of the quantum foam is almost exactly offset by some negative energy we don't understand. Either possibility is profound. The first means we're missing a deep principle of quantum reality. The second feels like the universe is balanced on a knife's edge. For no apparent reason, and this is where gravity's apparent weakness becomes central. To the fate of everything, that tiny leftover push, that one part in 10 to the 120. That's what we call dark energy. It's the dominant force now, shaping the large-scale future of the cosmos, deciding whether galaxies will drift apart into eternal darkness. So the feebleness of gravity isn't just about magnets and paperclips. It's about the vacuum itself. It's about why empty space weighs almost nothing gravitationally, when by all rights it should weigh everything. That silence, that near zero, it's what allows galaxies to form, stars to ignite, time to unfold. It's the quietest number in physics, and it holds the key to the ultimate destiny of all we see. Gravity might not be a force at all. It might be an illusion, that's the radical answer. It says gravity isn't fundamental. It doesn't exist at the most basic level. It emerges. It comes from the collective behavior of something deeper. Like a crowd's roar from thousands of voices, or temperature from the motion of molecules. You can't point to one molecule and ask for its temperature. That concept only makes sense for the whole group. So you can't find gravity in a single quantum particle. It only appears when you have a vast number of them, entangled in a complex network. This view is called entropic gravity. It's linked to the holographic principle. It turns everything on its head. It says what we perceive as gravity is a statistical tendency, a consequence of the universe's drive toward disorder, toward higher entropy. Think of a box of gas. The molecules spread out to fill the space. They aren't being pulled by a force. They're just exploring all possible arrangements. The most likely arrangement is a uniform spread. Now translate that to spacetime. Matter and energy arrange themselves to maximize entropy, to maximize the information content of the space they occupy. A massive object, like a planet, warps spacetime, not because it exerts a force, but because its presence is the most statistically likely configuration. For all the underlying quantum bits of information in that region, gravity in this picture isn't pulling. It's a thermodynamic gradient, an entropic force. Like the pressure that pushes gas to fill a vacuum, it's not fundamental, it's collective, and that elegantly explains its weakness, its unique character. At the microscopic scale, the other forces are doing the real work. The strong, weak, and electromagnetic forces. They are the particle-based interactions. Gravity doesn't exist there, because emergence requires a crowd. It requires a macroscopic scale. So its feebleness in the quantum realm isn't a puzzle. It's a prediction. It only gains strength when an astronomical number of quantum degrees of freedom become entangled over vast distances. Then, from their collective statistical behavior, the gentle curve of spacetime materializes. The force that binds galaxies together would be a side effect. a shadow cast by the deep, informational architecture of reality. It would mean the stage itself is built from the actors. And the pull we feel is just the universe tending toward its most probable state, its most entangled state. Our existence acts as a kind of filter on the universe. That's the anthropic principle. It moves past equations into something more like philosophy. It asks why the universe is the way we find it. It suggests the incredible weakness of gravity and all the other finely tuned constants might not be an accident. They might be a prerequisite, a condition that had to be met for us to be here asking, think about the balance. If gravity were even a little stronger, the effects would be huge. Stars would burn hotter and faster. Their lives would be short, over before planets could form, before life could start. And a stronger gravity would pull the universe back together more quickly. Everything would end before complexity could ever emerge. But if gravity were much weaker, its pull might never have overcome the initial expansion. Matter would just drift apart. A thin haze forever, no galaxies, no stars. The universe would be dark and empty, structureless, so gravity's precise, feeble strength sits in this very narrow window. A window that lets galaxies spin, lets stars shine for billions of years, lets planets form in stable orbits, lets chemistry slowly build toward life and consciousness. The anthropic principle changes the hierarchy problem. It says we shouldn't be surprised to find ourselves in a universe with these specific constants. We couldn't find ourselves anywhere else. This thinking fits with the idea of a multiverse. If our universe is just one bubble in a vast foam of universes, each with random laws, then most of those universes would be stillborn. Lifeless, but a tiny fraction, by pure chance, would have the right numbers for stars and planets and observers, and we would inevitably find ourselves in one of those rare, habitable bubbles. Our presence is the selection effect. So the weakness of gravity isn't a puzzle to be solved by a deeper theory inside our universe. It's just our cosmic address. The signature of the particular bubble we happen to emerge in. For many scientists, this is controversial. It feels like giving up on a causal explanation. It trades a how for a where, but as a framework, it's powerful. It shifts gravity from being a ghost in the machine to being the architect of possibility. Its silence isn't a flaw. It's the precise quiet that let the symphony of life begin. Its gentle pull wrote the rules for the stage. So while the search for a physical mechanism goes on, the anthropic principle offers a different answer. It tells us the force we see as weak is, in fact, perfectly tuned, not for elegance but for consequence, for us. To measure a whisper, you need a silent room. Henry Cavendish built one in 1798. His setup was simple: a wooden rod hanging from a thin wire, a small lead sphere at each end of the rod. Then he brought two large lead weights near the small ones. The gravitational pull between them was incredibly small, but it was enough to twist the rod, just a fraction of a degree. To see that twist, he fixed a mirror to the wire. He shone a light on it. The reflected spot of light became an amplifier. The tiniest movement of the mirror would send that light spot moving across the wall. That's how he measured a force weaker than the weight of a grain of sand. He called it weighing the world. He wasn't measuring the Earth's pull directly. He was measuring the pull between those lead spheres. From that, he could calculate the density of the Earth. And from that, the gravitational constant, g. That number, g, sets the strength of gravity in Newton's law. Cavendish found it with astonishing accuracy for his time. His experiment showed the true scale of gravity's weakness. It showed that the force that moves planets is, in a lab, just a delicate twist in a wire. Today, the work continues with more sensitive instruments. Modern torsion balances work in near-perfect vacuums. They're isolated from seismic noise, from temperature changes, from the Earth's own magnetic field. The goal is the same: to measure g more precisely. Yet after centuries, g is still the least precisely known of all the fundamental constants. We know the speed of light to many decimal places. We know the charge of an electron with incredible accuracy, but G is stubborn. Its weakness makes it vulnerable to every stray influence, every unseen vibration. This isn't just a technical problem, it's a fundamental statement. The force that shapes the cosmos is the hardest one to pin down in a lab, so we have to look beyond our planet. Scientists have put retroreflectors on the moon, arrays of mirrors left by the Apollo astronauts and Soviet missions. We fire powerful lasers from Earth at those mirrors. We time how long it takes for the light to come back, a round trip of about 2.5 seconds. By measuring that time with exquisite precision, we can track the moon's orbit down to the millimeter. This lunar laser ranging experiment is a solar system scale version of Cavendish's apparatus. It lets us test if Newton's G is truly constant. Does it change over time? Does it vary with distance? The results so far say G is stable to an incredible degree. But even a tiny, slow drift over billions of years would rewrite cosmology. It would mean the force of gravity in the early universe was different. That would change how stars formed, how galaxies assembled. A varying G is a direct window into physics beyond Einstein. So these painstaking measurements, from a quiet room in the 18th century to a laser beam crossing space, they're not just about refining a number. They are listening posts, straining to hear if the whisper of gravity has ever changed its tone. A change would be a crack in the foundation, a sign that the force we think we understand is still hiding its deepest secrets. That Electroweak hierarchy, it's a separate thing from gravity's weakness, but they are parallel. They point to the same place, the Large Hadron Collider. It wasn't just built to find the Higgs. It was built to find out why reality is stable. Because the Higgs mass, it sets the scale for the weak force, for all the other particles, and it's fragile. In the equations, quantum effects from the vacuum should push its value up, way up to the Planck scale. It should be astronomically heavy, but it's not. It's sitting at this much lower, gentle energy. That's the hierarchy problem. It's like a pencil balanced on its tip, staying upright for billions of years. Something has to be stabilizing it, and a lot of physicists think that something is a new symmetry, supersymmetry. It's an elegant fix. For every known particle, every quark, electron, photon, there's a hidden partner. A selectron for the electron, a squark for the quark, a photino for the photon. These partners have different quantum spins, and in the math, their contributions to the quantum vacuum would cancel out the wild fluctuations. The ones that threaten to inflate the Higgs mass. They'd give a natural reason for the weakness of the weak force scale. But here's the connection. If supersymmetry is real, and these particles exist, they should show up at energies not too far above what we've already seen. The tera-electronvolt scale. The same energy realm where, in theories of warped extra dimensions, the true quantum gravity scale might also be. So the hunt at the LHC isn't just for new particles. It's a dual search. One path looks for superpartners to explain why the universe didn't instantly collapse. The other path watches for microscopic black holes, or graviton-like resonances, hints of gravity's hidden strength. They're two threads from the same tapestry. The huge gap between gravity and the other forces, and the delicate balance of the electroweak scale. They might both unravel at the same time. In one collision, so far the superpartners haven't shown up. The data has pushed their possible mass higher and higher. That doesn't kill the idea, but it forces it into more complex forms. Each empty result is a message. The universe isn't as simple as our most beautiful theories hoped. But the search continues because the hierarchy problems are still there. They're the loudest signals we have that our map of reality is incomplete. Every time protons are smashed together at nearly light speed, we're not just breaking matter apart. We're testing the stability of space itself. We're asking if the silence of gravity and the quiet of the Higgs field are whispers from a hidden world. Just beyond our reach. The paradox is a furnace, it forges new ideas. Stephen Hawking showed that black holes aren't black, they evaporate. They give off a faint glow of radiation. But that creates a crisis. The radiation Hawking found is random, it's thermal noise, it carries no information about what fell in. If the black hole evaporates completely, all that information is lost. The details about stars, planets, books gone forever. That violates a sacred principle of quantum mechanics. Information must be preserved. You can scramble an egg, but in principle you could reverse it. The information is still there. Hawking's calculation said black holes burn the recipe. That's the information paradox. It pits our two most successful theories against each other. Quantum mechanics and general relativity in their most extreme arena. And its resolution is forcing a revolution in how we think about space, time, gravity itself. To solve it, we have to ask where the information goes. One radical answer is that it never actually falls in. The holographic principle suggests all the information about the black hole's interior is encoded on its surface. On the event horizon, like a cosmic scratch pad, the three-dimensional interior is a projection, an illusion from the two-dimensional data on the boundary. When the black hole evaporates, that information is slowly released back, released chaotically through subtle correlations in the Hawking radiation. The information isn't lost, it's transformed, it's been holographically stored and then retrieved. This idea turns gravity's strength into a question about information density. How much data can you fit on a surface? The answer from quantum gravity gives us the Bekenstein-Hawking entropy, a number proportional to the black hole's surface area. Not its volume, that's a profound clue. It suggests space-time and gravity are not fundamental. They are emergent. They arise from something more basic, quantum information. This leads to an even more startling connection. Captured by the slogan ER equals EPR, it links two ideas from Einstein. ER stands for Einstein-Rosen bridges. Wormholes, tunnels through spacetime. EPR stands for Einstein, Podolsky, and Rosen. They highlighted quantum entanglement, where two particles remain connected instantaneously across any distance. The conjecture says these are two sides of the same coin. A wormhole, a geometric bridge, is the physical manifestation of quantum entanglement. What looks like empty space between two entangled particles might, in the full description, be threaded by a microscopic wormhole. Not a tunnel you could travel through, a geometric representation of a quantum link. Think of it this way: space-time isn't a passive stage, it's a dynamic fabric. And the threads that weave it together might be quantum entanglement itself. Every bit of connected space could be held together by these invisible quantum threads. That gives a new perspective on gravity's weakness. If space-time is built from entanglement, then gravity's feebleness on small scales might reflect how quantum information is shared. At the quantum level, particles are entangled in a vast network. But that network doesn't generate a strong classical pull. It generates the gentle tendency for matter to come together. The tendency we call gravity. The force that crushes stars could be the same phenomenon that, on a microscopic scale, merely whispers. It's about the architecture of connections. So black holes, where gravity is king, are teaching us that gravity might be secondary, a consequence of the universe managing information. The event horizon isn't just a point of no return. It's the ultimate quantum hard drive. And the silence of gravity we experience here, far from any black hole, might be the quiet hum of that cosmic computer running, weaving the fabric of reality from a billion entangled threads. The early universe had this unimaginable energy. All the forces were one thing. There was a symmetry, then that symmetry broke. The single force split into the four we know. Gravity came away first, then the strong force, then the electroweak force split into electromagnetism and the weak force. That breaking of perfect unity released an immense amount of potential energy, and that energy may have triggered cosmic inflation. For a sliver of time, the universe didn't just expand. It exploded in size, doubling and redoubling faster than light. A region smaller than a proton was stretched larger than our entire observable universe. That solved puzzles like why the cosmos looks so uniform. But inflation may have done something else. It may have frozen the dials. The strengths of the forces as they emerged might have been fluid at first. Fluctuating, then inflation happened. It stretched spacetime so violently it locked those values in place, like a snapshot. The relative weakness of gravity could be a fossil from that instant. A number set by the dynamics of a scalar field, an inflattened field driving the expansion. As the universe inflated, that field settled into its lowest energy state. And in doing so, it determined the effective strength of gravity in the newly vast cosmos. In some models, this ties to extra dimensions. Imagine those extra dimensions are compact, curled up. Their size and shape determine how forces behave in our four-dimensional world. Inflation could have stabilized those dimensions. It could have chosen a particular configuration from a landscape of possibilities. A configuration where gravity appears incredibly weak from our perspective. So gravity's feebleness isn't an accident. It's a memory of the universe's most violent growth spurt. The force that feels so quiet now was present at the loudest moment. Its present strength is the echo of that first, defining shout. This divide isn't just a gap in the math. It's a crack in reality's foundation. On one side, you have the standard model of particle physics. It's a masterpiece of precision. It describes the strong force, the weak force, the electromagnetic force with breathtaking accuracy. It predicted particles like the Higgs boson decades before we found them. It treats the universe as a collection of quantum fields, and the particles we see are just vibrations in those fields. The math is built on probabilities, on discrete packets of energy, on uncertainty. It's the theory of the very small, and it works perfectly except for one thing. It has no room for gravity. The standard model's equations just don't include it. On the other side stands general relativity, Einstein's monumental theory. It doesn't deal with particles or probabilities. It describes gravity as the curvature of a smooth, continuous stage. That stage is spacetime. Mass and energy tell spacetime how to curve. And spacetime tells matter how to move. It's a theory of geometry, of the very large. It predicts black holes, the bending of light, the expansion of the cosmos, all with stunning success. But this beautiful, geometric picture is completely classical. It has no quantum uncertainty, no particles, no probabilistic fuzziness, so we're left with two rulebooks. One for the quantum world of atoms and forces, and one for the cosmic world of stars and galaxies. Both are spectacularly correct within their own domains. But they are written in different languages. They describe the same universe using incompatible logic. This isn't a minor technicality. It's a fundamental schism in our understanding of what reality is. And gravity's unique character is the fault line. The other three forces fit happily into the quantum framework. They have messenger particles. They play by the rules of uncertainty. Gravity resists. When physicists try to force gravity into the quantum mold, to describe it with a particle like the graviton, the mathematics breaks down. It produces infinities that can't be smoothed away. The equations scream that something is wrong. This refusal is a message. Gravity's weakness is a clue, but its mathematical stubbornness is a shout. It's telling us that spacetime itself, the very arena where all other forces play out, might not be what it seems. In general relativity, spacetime is a smooth, continuous fabric. But what if, at the tiniest possible scale, this fabric isn't smooth? What if it's grainy, discrete, made of tiny, fundamental units like pixels on a screen? This idea, called loop quantum gravity, suggests that space itself comes in indivisible chunks. There's a smallest possible volume, a smallest possible area. You can't divide space further. In this view, gravity's smooth geometry is an approximation, an average effect that emerges from this underlying quantum structure. Much like the smooth surface of a pond emerges from the chaotic dance of countless water molecules. Alternatively, gravity's resistance might mean it's not a fundamental force at all. Perhaps it's an emergent phenomenon, a collective consequence like temperature or pressure. Just as you can't point to a single air molecule and ask for its pressure, you might not be able to find gravity in a single quantum event. It only appears when a vast number of quantum degrees of freedom become entangled. From this complex network of information, the illusion of a curved spacetime materializes. This is the holographic principle in action. The force that binds galaxies could be a shadow cast by quantum data processing on a distant boundary. So the incompleteness of the standard model isn't a failure. It's a guidepost. Its silence on gravity is the loudest hint we have. It points beyond particles and fields, toward a deeper layer of reality where geometry and information are the primary ingredients. The quest to unify gravity with quantum mechanics isn't just about making the equations work. It's a search for the true language of the universe, a language that can describe both the dance of a photon and the curve of a cosmos with the same elegant set of rules. Until we find it, gravity's gentle, persistent whisper will remain the most profound question in physics. Looking for a whisper means you need the loudest events out there. We can't build a collider the size of a galaxy, so we have to find one nature already made. The search for quantum gravity moved from the lab to the telescope. Now scientists look for the faintest scars, tiny cracks in the smooth predictions of Einstein's relativity, things that could only come from gravity's quantum nature. These aren't gravitons you can catch. They're subtle violations of rules we take for granted. One of the most sacred principles is Lorentz invariance. The idea that physics is the same for everyone, no matter how fast they're moving. The speed of light is constant, but some quantum gravity theories say at the tiniest scales that symmetry might fray. Just a little. If spacetime is grainy or foamy at the Planck scale, it might treat different light energies differently. A high-energy gamma-ray photon, vibrating with tremendous frequency, could interact with that microscopic foam in a way a low-energy radio photon wouldn't. Over cosmic distances, that tiny interaction could add up. A gamma-ray burst from billions of light-years away might arrive with its highest energy photons delayed. A fraction of a second behind the lower-energy ones, a staggeringly small delay. But if you could measure it, it would be a direct signature, a fingerprint. So astronomers watch the most violent explosions, gamma-ray bursts, the birth cries of black holes, or the furious jets from supermassive black holes in distant galaxies. They dissect the light from these events across the whole spectrum, from radio waves to tera-electronvolt gamma rays, looking for that telltale lag. The silence so far is its own data. It tells us if space-time foam exists, its grains are even finer than we thought. Another place to look is the oldest light. The cosmic microwave background. That faint, cold glow is the afterimage of the Big Bang, a snapshot of the universe at 380,000 years old. But the patterns in that light, the tiny temperature variations, were imprinted much earlier, during inflation, when the universe was smaller than a proton. When quantum gravity effects should have been dominant, the swirls and spots in that microwave background might hold frozen echoes, specific patterns, or a preferred direction in the polarization of that ancient light could be a relic. It's like looking at a frozen lake for the preserved imprint of the first pebble that ever disturbed the water. The challenge is always gravity's weakness. Any quantum signature gets drowned out by stronger processes. That's why we need the most extreme laboratories, event horizons of black holes where gravity traps light. That's where quantum effects should be most pronounced. The mysterious glow of Hawking radiation, if we could ever detect it, would be a direct probe. Quantum fields in curved spacetime. The violent collisions of neutron stars shake spacetime to create gravitational waves. Another testbed. As those waves travel, could a quantum graininess leave a subtle distortion in the signal? Every new observatory is a quantum gravity experiment. Gravitational wave detectors, ultra-high-energy gamma-ray telescopes. They're all listening for the same thing. For the moment, the smooth geometry of general relativity stutters. For the instant, the universe's rulebook shows a penciled-in footnote written at the Planck scale. We're using the cosmos as our accelerator, its most energetic tragedies as our data points, hoping in that immense violence we might finally hear the quiet click of gravity's true quantum nature. The constants we measure now might not be permanent. Gravity could have changed. The idea is a varying gravitational constant, a g that shifts slowly over time. It's a profound thought. The strength of the force holding everything together might not be a fixed number. It could be a dial slowly turning. If that's true, the laws of physics have a history. They evolve, and the weakness we see today might just be a snapshot, a single frame in a much longer film. To test this, you need cosmic timepieces, clocks that have been ticking since the universe was young. One of the most precise is the orbit of our moon. For over 50 years, scientists have been firing lasers at those retroreflectors left on the surface, timing the light's round trip to the millimeter. That lets them track the moon's motion with unbelievable accuracy. Any slow drift in the strength of Earth's gravity, or in G itself, would show up as a subtle anomaly in the lunar orbit. The moon would be slightly ahead or behind where Newton and Einstein predict. The data so far is clear. G is constant to within a vanishingly small margin. It hasn't changed measurably in the half-century we've been watching, but you need to look much further back. To do that, you use natural clocks, pulsars. The spinning corpses of massive stars. These neutron stars rotate with metronomic regularity, beaming out radio pulses. Some pulsars are in binary systems, orbiting another star or another neutron star. The dance of these incredibly dense objects is a perfect gravity lab. The timing of their pulses, the decay of their orbits from gravitational waves, all of it depends on the strength of gravity. By studying pulsars billions of years old, you can probe whether G was different when they formed. Again, the answer is a tight constraint. No significant change has been detected over these cosmic timescales. Yet the possibility remains, because even a variation too small for our instruments to see could have shaped everything. Rewind to the first few minutes after the Big Bang. The era of Big Bang nucleosynthesis. This is when the first atomic nuclei formed. Protons and neutrons fused into deuterium, helium, a trace of lithium. The rates of those nuclear reactions and the final abundances depended critically on how quickly the universe was expanding, and the expansion rate was governed by gravity. The strength of gravity pulls on the cosmic fluid, trying to slow the expansion. If gravity were even a fraction stronger back then, the universe would have expanded more slowly. That would have left more time for nuclear reactions. More hydrogen would have been cooked into helium. The observed cosmic abundance of helium is a precise fingerprint. It tells us that gravity's strength during those first 3 minutes must have been almost exactly what it is today. Later, as the universe cooled and dark matter began to clump, gravity's strength set the pace for the formation of the very first structures. If gravity were stronger, those first stars and protogalaxies would have assembled earlier in a denser, hotter universe. The entire cosmic history of galaxy formation would be shifted. You can look at the most distant quasars, the oldest galaxies we can see, and compare their properties to simulations. Their existence, their sizes, their ages, they all place another tight lock on the possible variation of G. So why does the idea persist? Because it offers a potential escape from fine-tuning. If the constants can evolve, then the incredibly precise values we see today might not be an accident. They could be the outcome of a dynamic process, a universe that naturally settles into its current state over billions of years. In some theories, like scalar tensor cosmology, the gravitational constant is tied to a cosmic field. As that field evolves, G slowly changes, approaching the constant value we measure now. The weakness of gravity today could be the end point of a long relaxation. This ties the mystery directly to the life story of the cosmos. It suggests we shouldn't just ask why gravity is weak. we should ask how it became weak. The silence we measure in our labs might be the mature, quiet state of a force that was once louder, more active, in the fiery youth of the universe. Every constraint from the moon, from pulsars, from ancient helium, is a chapter in that biography. They are the lines that tell us the plot hasn't changed dramatically. But between the lines, in the spaces of unimaginable subtlety, the story of gravity's strength might still be quietly unfolding. That gap between gravity and the other forces. It's a signpost. It points to a frontier, and this hierarchy problem, it's not just a curiosity, it's a crisis, a fundamental crisis in how we describe reality. And it demands a revolution. For a century, physics moved forward by going smaller, higher energies, but this problem tells us the next leap might not come from a bigger collider. It might need a new perspective on space, on time, on what matter actually is. Think of our theories as a map. It describes continents we know, the realm of particles, the realm of stars and galaxies, but between them on the map there's this vast ocean, an empty ocean, marked only by a question, the question of why the forces have such different strengths. That ocean isn't empty because nothing's there. It's empty because we lack the concepts, the language, even the right kind of boat to explore it. The hierarchy problem is the compass. It points straight into that unknown. Every proposed solution, extra dimensions, supersymmetry, it's an attempt to chart that ocean, to build a vessel that can cross it. These aren't wild guesses. They're rigorous mathematical responses to a precise puzzle. The fact that gravity is 10 to the 36 times weaker than electromagnetism. That's not a vague observation, it's a specific coordinate. A set of numbers any theory of quantum gravity has to reproduce, has to explain. That's why the search is so urgent. The answer won't just fill a blank on the map. It'll redraw the coastlines of everything we think we know. If extra dimensions are real, our three-dimensional existence becomes a slice of a richer reality. If supersymmetry is found, we double the particles. We discover a hidden symmetry that stabilizes the cosmos. If gravity is emergent, then space-time becomes secondary. An illusion from a deeper quantum network. The experiments are our most ambitious. Silent torsion balances measuring gravity at the width of a hair. Colossal colliders smashing protons. Searching for new symmetries, for hidden dimensions. Telescopes looking for echoes of the Big Bang. They're all listening for the same signal, for the whisper that explains the silence. So this quest to understand gravity's weakness, it's not an academic sideshow. It's the central plotline of 21st century physics. It's the mystery that forces the question. Are our basic assumptions about reality correct? Are we missing entire dimensions? Is the universe built on information, not matter? Does gravity have a history? A different beginning. Each answer feels like science fiction, but each one is a direct, logical consequence of trying to solve this one persistent riddle. The future of physics will be written by those who sail into that ocean, who take the hierarchy problem not as a dead end, but as the most important clue we have. The gentle pull holding you in your chair, that force that seems so simple, so quiet, it's orchestrating the next revolution in human thought. Its very feebleness is the beacon, calling us toward a deeper vision, a stranger one, a more unified vision of the cosmos. This quiet force raises a question bigger than physics. It brings up a kind of wonder, somewhere between science and philosophy. Why are the numbers in the universe exactly what they are? The incredible weakness of gravity, the precise mass of the electron, the exact strength of the nuclear forces. These are like dials on a cosmic control panel, and they're all set to values that make complexity possible. Stars that last for billions of years, planets with stable orbits. Chemistry intricate enough to build a living cell. That's the fine-tuning problem. To a lot of people, it feels like a signature, like a hint of purpose or design in the architecture of everything. It can feel like the universe knew we were coming. But science has another story, one with breathtaking scope. The multiverse. If our cosmos is just one bubble in an infinite foam of universes, each with random physical constants, then most of those bubbles are stillborn. Dark or empty or collapsing instantly. But by the sheer law of large numbers, a few will, by pure chance, have the right combination, the right dial settings. And in those rare, habitable bubbles, observers will eventually arise. They'll look out and marvel at how perfectly tuned their world seems. We would inevitably find ourselves in such a place, because we couldn't find ourselves anywhere else. That's the anthropic principle. It shifts the question from why is the universe fit for life, to where in the landscape of all possible universes does life find itself. It trades a why for a where, and that changes the weight of the mystery. Gravity's profound silence isn't a puzzle to be solved inside our universe, it's our cosmic address. The quiet corner we happen to inhabit. This perspective is humbling and it's liberating. It suggests our most cherished theories, our maps of reality, are just that, maps. Brilliant human constructions that work remarkably well within our local territory. But they may not describe the whole continent. The principles that govern the multiverse, the reason for the landscape itself, might be forever beyond our reach. Our intuition, built in a world of medium-sized objects moving at slow speeds, may just fail when confronting the foundational logic of all existence. That's the true gift of this mystery. It's a lesson in humility. The force that feels absolute, the pull that anchors your world, is revealed as a delicate balance. One possibility in a sea of countless others. It reminds us that science isn't a collection of final answers. It's a sustained act of curiosity, a conversation with a universe that is far stranger and far more generous with its mysteries than we often dare to suppose. We are here asking these questions because gravity is weak enough to let stars burn long, and strong enough to gather them into galaxies. Our very existence is woven into that specific, quiet number. And in pondering it, we're not just studying physics, we're contemplating the conditions of our own story. The hunt for gravity's secret is a race against our own limits. We're trying to hear a whisper from across a chasm, and our ears are only so good. That same weakness that defines the mystery makes it hard to investigate. But that's not the end. It's a call to build better instruments, to think differently, to use the whole universe as a lab. Our technological limits today are just the boundary for tomorrow's discovery. The next experiments won't just refine numbers. They'll look for new signatures, for cracks in the cosmic facade that only the most sensitive eyes can see. Think about the quiet of space. Freed from Earth's seismic rumble, a new kind of observatory is taking shape. The Laser Interferometer Space Antenna LISA would place 3 spacecraft millions of miles apart, forming a triangle of laser beams. A gravitational wave observatory on a staggering scale. Current detectors on Earth hear the final, violent mergers of black holes and neutron stars, but LISA would listen to a different frequency. It could detect the gentle, persistent hum from millions of binary stars across the galaxy. It might catch the faint echo of cosmic strings, hypothetical defects in spacetime from the universe's first moments. Or the ring-down of exotic compact objects, theoretical remnants even stranger than black holes, whose waves would carry the imprint of quantum gravity. In the silence of orbit, LISA wouldn't just listen for events. It would listen for the background music of spacetime itself, a music that may hold the key to gravity's first principles. Back on Earth, the search moves into the realm of breathtaking precision. Atomic interferometry uses the wave nature of atoms to measure gravity. You drop clouds of ultra-cold atoms and split them with laser pulses, creating an exquisitely sensitive ruler. The falling atoms act as test masses, and their quantum interference pattern reveals tiny differences in gravitational pull. Future experiments aim to test the equivalence principle, the idea that all objects fall at the same rate, the cornerstone of general relativity, with an accuracy 100 times better than ever before. They'll compare how different materials fall in a vacuum, If a block of platinum and a block of titanium accelerate toward Earth at even a minutely different rate, it shatters Einstein's theory. It points directly to new forces or to subtle interactions with hidden fields or dimensions. It's a search for a violation of a fundamental symmetry conducted in the quiet fall of atoms. Then there are the more speculative, high-energy frontiers. If large extra dimensions exist, the true quantum gravity scale could be within reach of future particle colliders. In that scenario, smashing protons together at even higher energies could, for a fleeting instant, create not just new particles, but microscopic black holes. These wouldn't be the monstrous entities of astrophysics. They'd be quantum entities, evaporating instantly into a shower of radiation. Detecting them would be a direct portal into the geometry of hidden dimensions. Similarly, careful analysis of particle collisions could reveal subtle deviations, a slight excess of events, in a certain direction, hinting that a graviton has briefly leaked into an extra dimension before snapping back into our own. These aren't guaranteed discoveries. They're long shots, but they're testable long shots. They turn the most abstract theoretical ideas into concrete predictions that machines can hunt for. Each of these experimental frontiers, from the orbital ballet of Lisa to the quantum fall of atoms, represents a different strategy for listening to gravity's quiet voice. They're not competing ideas. They're a coordinated assault on the mystery from every possible angle. Technological progress, in this light, isn't just about building faster computers or more powerful engines. It's the act of forging new keys for cosmic locks. It's how we extend our senses into the dark, hoping to feel the shape of what we can't yet see. The profound weakness of gravity forced us to build these incredible tools. And in building them, we may finally turn its silence into the clearest message of all. There's this one equation, a single master principle, something that could give you all of physics. That's the dream, unifying the four fundamental forces into a single theory, a theory of everything, a framework that describes quantum particles and the curve of spacetime with the same mathematics. But there's a block. One profound fact: gravity is staggeringly weak. It's the outlier, the rebel force. It won't fit into the quantum rulebook. So any successful theory can't just include gravity. It has to explain why gravity is so gentle, why it's 10 to the 36 times fainter than electromagnetism. The solution has to make that gap feel inevitable, a natural consequence of some deeper, hidden logic. The leading candidates go into profound strangeness. String theory says the fundamental ingredients aren't point-like particles. They're tiny, vibrating loops of energy. These strings exist in a universe with more than 3 spatial dimensions. The different vibrations of a string correspond to different particles. A photon, a quark, a graviton. In this picture, gravity's feebleness could come from the geometry of those extra dimensions. Maybe the strings that make gravitons vibrate throughout the full, higher dimensional space. That would dilute their influence from our 3-dimensional perspective. Or maybe they're confined in a specific way by the warping of that space. The hierarchy becomes a geometric artifact. Not a fundamental mystery, loop quantum gravity takes a different path. It suggests spacetime itself isn't smooth. It's woven from a network of discrete, quantized loops, pixelated at the tiniest scale. In this view, gravity isn't a force mediated by a particle. It's a direct manifestation of this evolving quantum geometry. Its apparent weakness on large scales could be a statistical effect, emerging from the collective behavior of trillions of these fundamental spacetime threads. The quiet pull we feel would be the average, the macroscopic average of a furious, microscopic quantum weave. Other ideas go further. Some propose our universe is a simulation, running on a cosmic quantum computer. Gravity would be a kind of thermodynamic force from information processing limits. Others suggest gravity isn't fundamental at all. It's an emergent phenomenon, like fluid flow or temperature, arising from the entanglement of quantum bits. In each case, the challenge is the same: The theory has to start from a simple, unified premise. Then, through its own internal logic, generate the wild diversity we see. It has to show how the roaring symphony of the strong force and the faint whisper of gravity are just different notes, played on the same instrument. Achieving this would be more than a scientific breakthrough. It would be a monumental leap in understanding, a triumph of pure reason, revealing a hidden simplicity beneath the complexity of the cosmos. It would answer the child's question, why a magnet can beat the whole Earth, not as a curiosity, but as a necessary feature of reality's deepest architecture. The search for this theory is a testament to stubborn curiosity. We're piecing together a puzzle where the final picture is unknown, guided only by the shape of the pieces, and the most puzzling piece is the gentle, persistent silence of gravity. The most radical ideas start by taking apart the stage itself. If gravity's weakness is the deepest clue, then maybe we've been reading it wrong from the beginning. Maybe it's not a force to be unified, it's an illusion to be understood. That leads to the holographic principle, a concept so counterintuitive it reshapes reality. It says all the information inside any volume of space, every star, every atom, every ripple of gravity isn't truly three-dimensional. It's perfectly encoded on the two-dimensional boundary around that volume. Think of a hologram. The three-dimensional image you see floating isn't built from stacked layers. It's projected from flat, two-dimensional film etched with interference patterns. In the same way, our whole cosmos, with its gravitational fields and swirling galaxies, might be a projection, a cosmic hologram. The true theory of everything would live not in the volume we experience, but on a distant, enclosing surface. Gravity, in this view, is not a fundamental force. It's an emergent property, a consequence of how that encoded quantum information on the boundary interacts and entangles. Its incredible weakness becomes a natural feature. Because in the translation from a fundamental two-dimensional quantum theory to our perceived three-dimensional world, the strength of interactions gets diluted. Gravity's feebleness is the signature of that projection. It's the hint that we are living inside the projection. Other frameworks go further, into a realm called pregeometry. Here, the goal isn't to quantize space, but to build it from scratch. The idea is that space and time are not the starting points. They are not the canvas. They are the painting. What comes before geometry? The candidates are abstract, non-spatiotemporal building blocks, quantum bits of information buzzing with no inherent location. Or a causal set, a vast collection of discrete events with only a bare before and after relationship, not yet woven into a continuous fabric. From the complex network of connections between these primitive elements, the familiar smooth continuity of spacetime is thought to emerge. Like the illusion of a flowing movie from a sequence of still frames. In such a theory, gravity is not something that curves a pre-existing stage. Gravity is the leftover signal, the collective behavior, of that underlying network finding its most probable state. Its weakness is not a parameter you dial in. It's a number that simply falls out of the mathematics of emergence, a number that tells you how efficiently that network encodes our perceived reality. These aren't just wild speculations. They are rigorous, mathematical responses to the dead ends of more conventional approaches. They take the hierarchy problem and turn it inside out. The problem isn't that gravity is oddly weak compared to other forces. The problem is that we mistakenly think of gravity as being the same kind of thing as those other forces. In a holographic or pregeometric universe, the question changes. We stop asking why gravity is 10 to the 36 times weaker. We start asking what the fundamental degrees of freedom are, and how their dynamics inevitably produce something that looks, at our scale, like a very faint geometric force. The silence of gravity becomes the most important evidence we have that space, time, and force are not fundamental. They are derived. They are the language our minds use to describe a deeper, stranger symphony playing on instruments we have not yet seen. This points toward a future physics where the stage itself is the final actor to take a bow. revealing a more primitive reality waiting in the wings. The silence of gravity is a signature. It's a fingerprint left on our universe by something deeper. And this mystery, its profound weakness, that's not a minor detail. It's a fundamental clue. A clue about the architecture of reality. It touches the geometry of hidden extra dimensions. It connects to the quantum emergence of spacetime from a sea of information. It ties into the cosmic history of inflation, the possibility of life in the cosmos, from that number, a 1 with 36 zeros, to the frontiers of holography and pregeometry. This single puzzle challenges the bedrock of physics. It forces us to question our basic assumptions: what a force is, what space is, what the universe is made of. This mystery also inspires our greatest ambitions. It drives us to build instruments of impossible sensitivity, to listen for a whisper. It pushes us to conceive of colliders that might one day touch the fabric of spacetime. It compels us to use the entire cosmos as a laboratory, studying the oldest light, the most violent collisions, looking for a faint crack in Einstein's elegant geometry. The quest to understand why gravity is so weak, that's more than a technical problem. It's a story of human curiosity, looking at a magnet lifting a paperclip and seeing a window. A window into the hidden dimensions of creation. As we test and theorize and wonder, remember this: the gentle force holding your feet to the ground. The same force that guides the planets in their silent orbits. That's not just a fact of life. It's a question, and that question is the key. It may be the master key. The one that finally unlocks the universe's deepest, most guarded secrets.